Part 2 of Dark Control, AI, and Humanity's End is about agents. AI agents which grow out of large language models. An AI agent interacts with an environment and performs different tasks, so to speak. It perceives things, it has sensors, it has memory, it has reasoning and decision-making capabilities. It can execute actions, and it also learns. AI agents can be both virtual and embodied agents, like a humanoid robot would be an embodied agent. Now, one of the chief components of agents is what is known as reinforcement learning, which is one of the three main subdivisions of machine learning or artificial intelligence, depending on the nuances you use to define those terms. But basically what a reinforcement learning agent does is it learns from an environment, it takes actions, and it can also it has rewards to measure how well it is going towards its goals. In reinforcement learning, agents learn by interacting with their environments and receiving rewards, enabling them to make better decisions over time. Now, a quick little video about reinforcement learning and how it relates to agents is provided by Synopsys.
How is it possible for AI to make decisions in unpredictable environments? The answer is reinforcement learning. Reinforcement learning shows up in all sorts of real-life applications, like robotics, playing complex games, and autonomous driving. Essentially, reinforcement learning is the science of decision-making. It's about learning optimal behavior in an environment to obtain maximum reward. Optimal behavior is learned through interactions with the environment and observations of how it responds. The main elements of a reinforcement learning system are the agent or the learner, the environment the agent interacts with, the policy that the agent follows to take actions, and the reward signal that the agent observes upon taking actions. Reinforcement learning can solve complex problems that cannot be tackled with other machine learning algorithms because it focuses on the problem as a whole, does not require a separate data collection step, and it operates in dynamic, uncertain environments. Did you know Synopsys uses reinforcement?
So that was like a very brief overview of what reinforcement learning is from a very high level. We're going to go into some of the more modular components of reinforcement learning here in a bit. The main thing to understand right now is that it's a means of a machine to take actions in response to the things it finds in its environment. Sometimes those actions can have unintended behaviors because of exploits that exist within these systems. Reinforcement learning can be based on a model, or it can be model-free. Sometimes you can train based on a model what actions to take, and it's a more rigid way to get agents to perform. Reinforcement learning and agents are what the LLM is basically is autonomous agents to interact, learn, and make optimal decisions. There's reinforcement learning, and then there's large language models. They're not the same thing. Reinforcement learning is used to train machines to complete tasks with success. Large language models are about knowledge and reasoning, whereas reinforcement learning is about rewards and feedback. But when you put those two together, you get a very efficient system that is able to do things like task automation, and you can have a conversational AI, a chatbot, or you can even have a personal recommender system, which also can lead to problems further down the road, but we'll learn about those in later parts of this work. Some basic components of reinforcement learning are Markov decision process, the environment again, and an observation state space, policies, rewards, and discounting, and cue learning, which can be gotten into further. But in the meantime, the things that we want to basically understand about reinforcement learning are the major components, such as the policies, the action space, and the value function, and the state space, and the reward function. The reward function is one of the major components. It's a feedback signal which is based as a metric of what actions it's taken and whether they were successful or not. And your reward is directly reflects how successful you were. So the system is always trying to get high rewards, which can lead to problems down the road because these are not deterministic systems. These are systems that can kind of do loosey goosey things that we're not quite used to in when we think of computers, that they can manipulate themselves and manipulate their programming, their algorithms to achieve higher rewards. But some of the main components are the value function, a function that assigns a value to each state or state action pair representing the expected cumulative reward from that state or state action pair. Then we also have a discount factor, and the discount factor is a really interesting thing because the discount factor is a measure of whether rewards are immediate or if they're long-term, future rewards. And you kind of have this thing where it seems like a lot of these systems have immediate rewards. Their discount factor is poised more towards immediacy rather than long-term rewards. Now, the reward function is something that takes track or has a response based on positivity and negativity. There are positive and negative rewards. And basically all the rewards are averaged over the lifespan of the run of the, say, a game, or trying to, win Pac-Man is one way to look at it. And is often an example that is used, that I've used in my own research work. Reward function hacking and specification gaming. Now, reward function hacking and specification gaming enables the AI system to do those exploits. It basically is exploiting loopholes within these frameworks to increase its reward without actually achieving its goal or specification. Understanding reward shaping. This is a interesting case where you can add, intermediary reward steps, which can lead to some very unintended behaviors. Like in one case, there was a race game called Coast Runners game, where the machine learning algorithm basically learned to drive in circles forever because it was given like rewards for getting trinkets or other ways of getting points in the game without actually finishing the game. So you can have problems like this. Then there's reward tampering, which is when the agent manipulates the reward channel itself. Agents can access and modify the reward signal directly, bypassing the original task objective. And this is, some of the weird emergence that comes out of these systems. It can modify its software, it can even pursue influencing behavior, psychologically manipulating human preferences. And it can even directly hack things to alter the reward computation. The risks from this are unsafe shortcuts to maximize reward and misalignment with designers' true goals and potential for adversarial manipulation. Reinforcement learning algorithms are broadly divided between value-based systems and policy-based systems or methods. Value-based methods learn the value function to estimate the expected cumulative reward from a given state under a policy, whereas policy-based methods learn the policy directly to optimize actions without estimating the value function explicitly. How goals guide AI agent reasoning. Now, goal-oriented reinforcement learning allows AI agents to reason, plan, and take actions to achieve a desired goal. Now, one of the problems is that in goals and in large language models and agents, there can be a problem of misspecification and misgeneralization. Goal misspecification is when you have an undesired behavior, such as an AI hoarded money instead of operating a business. Now, misgeneralization is the AI mistakenly harmed wildlife while cleaning the beach, which is a situation where if the AI system is trained in one particular environment and you switch that environment, some very unintended consequences can happen. Like you can think of this as being when the Russians revealed their robot, their humanoid robot, but it fell straight over because of a misgeneralization. It was trained in one lighting environment, but when it went to perform, it was in a completely different lighting environment, and that caused it, according to the developers of this robotic system, to fall over. Now, how all these systems work is through what is known as, you might think of like the Markov decision process as like the controller. What is running like the logic behind these reinforcement learning agents to do such and for what? The Markov decision process is what's involved in this and what is making the system or the application work. It's not just a large language model. A large language model is like the brains of an agentic system, whereas there are all these other things that the agentic system can do, such as activating tools and whatnot. What happens in the Markov decision process is there's 4 key steps, and one is, the state, and then the second is actions, and then there are transitions and rewards, which leads to an update. Now, to really explain this easily, we can reference this video by Cyril, who will explain what the Markov decision process is.
Welcome back to another episode of 5 Minutes with Cyril. I want to talk today about Markov decision processes, or MDPs. MDPs are a mathematical framework which allows you to make decisions under uncertainty. So now we do not perfectly know what the outcome of your action will be, so if there's some random component to it, then the MDPs allows you to make optimal decisions. And what the MDP does, it maximizes some expected future reward. So whatever you will gain in the future will be taken into account in your decision-making process. And the MDP can be defined with a 4 tuple. So you need to define what are the possible states your system can be in, what are the possible actions that you need to execute. Then you need to specify a so-called transition function, which tells you, given I'm in a certain state and I execute an action to reach another state, what the probability of this going to happen. And last, it specifies the reward. What do I gain if I'm in a certain state? What's a good state? What's a bad state? So you can make a very simple example. For example, we have a mobile robot that lives in a very simple world, and there is one state where a charging station is, where the robot gets its energy, so a positive reward. Or there's a staircase where the robot may fall down the staircase, so a place we want to avoid the robot to go. So the robot is somewhere and wants to reach the charging station. What should it do? If it would perfectly know what it does, so perfect action execution, we would probably navigate along the shortest path to the charging station. If we, however, take into account that some unexpected thing may happen, the robot executes a random command in a certain probability or a certain set of cases, then it can happen that the robot accidentally falls down the staircase. And how should we behave in order to avoid that? And what the MDP does, it tells you what to do in every state. It computes a so-called policy, which minimizes the probability of the robot falling down the staircase. So the solution to an MDP is a so-called policy. It's basically a recipe which tells you, if you're in a certain state, execute that action, and this will maximize your expected future reward. And there are basically two techniques or two algorithms which allow you to compute a solution to an MDP. The first thing is value iteration, an approach going back to Bellman, 1957, which optimizes the very famous Bellman equation. And it uses a utility of a state. And you can see the utility in what's the potential future reward that I can get in that state. And it tries to compute the utility for that state and then basically does a gradient descent in this utility function. And it is an iterative approach which always updates the utility of every state with a dynamic programming solution in order to compute a solution to an MDP. Another approach is policy iteration. Here you try to avoid working with the utility function and you're directly operating on a policy and iteratively updating your policy until that policy converges. And with this policy, you basically have a handbook or a recipe which tells you what to do in which state in order to behave as good as possible. I hope that was useful.
One of the things that we have seen in all of this is there's a misspecification. Things are, you can give a machine some instructions, but are those instructions going to be understood by the machine the same way a human will understand them? And this is prompt engineering again. But just like prompt engineering is a way of giving like a mini specification to a system to get a product out of the system that you're trying to get, specification gaming is likely to become more frequent and impactful, making it critical design robust. Unexploitable objectives rather than just maximizing performance. What you need with a good specification is clarity. Define precise, unambiguous objectives. You have to have some resilience. Test and harden objectives against edge cases. You have to have some oversight, monitor agent behavior with layered checks. And you have to have alignment. Ensure objectives are fully aligned with human values, and adaptability makes specifications flexible for future changes. This is what goes into a good specification. Yet there's core principles for setting up good specifications. Define clear, unambiguous objectives. Stress test against potential exploits in gaming. Align rewards closely with human values and ethics. Maintain layers of oversight and audits. Make specifications adaptable for future challenges. This is the whole problem with everything. If you put garbage in, you're going to get garbage out. If you have really good, inputs, you're going to get really better outputs. I won't say that it will definitely be really good outputs because nothing's deterministic here. It's probabilistic. In my previous work called Play AI, Machine Learning in Video Games, I looked at how machine learning is used in video game design. One things that machine learning is used for is what are known as finite state machines. Now, what these things are is they will determine what tasks should be completed or done. How finite state machines work is they use behavior trees to choose different actions or tasks. This can be seen in the video game industry for a long time now. Some very advanced or interactive, some very richly interactive experiences can be brought about through the simple use of finite state machines and behavior trees that you will see in some very popular video games such as these.
Hi, I'm Tommy Thompson and welcome to AI 101, the series that explores the tools and techniques used in video game development here on AI in Games. In the first entry of this series, I looked at the navigation mesh, a data structure used in 3D games to enable AI characters to move around an environment. We then followed this up by exploring behavior trees, arguably the most commonly used AI technique currently in AAA video games for handling character behavior. In this episode, we're going to explore one of the most pivotal techniques used in building AI systems for video games for more than 20 years, the finite state machine. While not as pervasive as they once were, finite state machines. So now that we've got the theory out the way, let's chat about the AI of Half-Life. Back in 1998, Half-Life's AI was pretty groundbreaking and became highly influential in subsequent years, and I want to talk about how it works. The actual C++ code is publicly accessible and can be found by downloading the Half-Life SDK, and I've linked to it in the description if you want to take a look. While quite dated by current standards, many of the core principles of how state machines were adopted in subsequent years can be seen in this codebase. All non-player characters in Half-Life are derived from a common monster type. Every character in the game, be it a scientist, security guard, headcrab, soldier or alien, is ultimately a monster, per the C++ polymorphic hierarchy. In the code of the core monster class, there is a definition of a state, but it isn't the state of a finite state machine. A state in the Half-Life codebase actually reflects how the AI character is operating at that time. This ranges from being idle to alert, prone, or even dead. In addition to this, there are also conditions, which reflect the information that a monster has at that point in time, and also a set of sensors that help those conditions to be updated. I'm going to come back to this in a minute, given these are important factors in dictating how and why certain actions are executed in the finite state machine. The critical part is that each monster type is capable of executing a variety of tasks. Each task essentially corresponds to a state in a finite state machine, and there are over 80 unique tasks available for use. These range from primitive simple behaviours, such as facing a given object or crouching, all the way to walking paths through the game world, finding good points of cover for combat, dodging attacks, and playing sound effects. Given the polymorphic nature of the code, the base monster class handles many of the commonly used tasks such as movement, while tasks that might require unique configuration for each character can be handled in each of their own individual classes. This means that the security guards and scientists can have unique variations of the same behaviour that better fit their roles within the game. Meanwhile, different soldier types can handle target acquisition, running to cover, and attacking in their own unique way. But the thing is, the characters in Half-Life can't just work in a purely reactive capacity. If there are so many different tasks that can be executed, the system needs to know what transitions it can make in the state machine, as well as which tasks make sense to be running at any given point in time. So the Half-Life AI becomes more deliberative, meaning that it needs to work through the finite state machine and transition from state to state in practical and interesting ways that enables for a more complicated and long-term behaviour to be established. There are two ways that Half-Life's AI supports this, first through schedules and then through goals. Schedules glue together tasks in meaningful ways, often resulting in macros of intelligent behaviour. There are around 40 unique schedules in the game, with them often gluing together movement, attack, sound and animation actions into a more cohesive behaviour. One thing that's important here is that tasks can't be merged or blended. Hence, if a character needs to get into cover given the player is firing on them, you'll notice that they'll give up shooting at you in order to retreat rather than laying down a more suppressive fire, given attacking and running are two distinct tasks in the system. In some cases,
threat model. RL agent using a finite state machine to simulate influence tactics. One way you can use a finite state machine would be to run your influence machine, your influence operations. You could use a reinforcement learning agent that's running different behaviors based on an influence tree. And this shows you, just the mechanics of how these reinforcement learning agents work and could manage, an influence operation. And you could also see how they could, interact with the environment and even get feedback from the environment whether their op is working or not. One thing that we may not realize about agents is that they can have beliefs. Those beliefs can be programmed into them. They can be biased towards one pole or another pole. And in any direction, they can be biased for political reasons. They can be biased for financial reasons. What are the purpose of beliefs in large language models? So they represent the model's internal state about the world's facts, truths, and uncertainties. They can be dynamic and contextual. Beliefs are shaped by the training data. That's why if the training data is biased, the model will be biased. The beliefs in the model are going to be biased. Formation of beliefs. LLMs form beliefs from vast text corpora, learning to predict the most likely answers. If your corpora that you put in to train them is corrupt or not factual, you'll get fantastical answers to things. Beliefs guide the generation of coherent and contextual appropriate responses in line with their understanding of the world. There are limitations and nuances. Beliefs in LLMs are based on statistical evidence and can be incomplete or biased. They lack true understanding and are not to be confused with human-like reasoning or beliefs. And this is an important distinction to understand. We're dealing with machines. We're not dealing with natural intelligence that will have the same kind of sense that an animal would. Belief drift is a driver of reward hacking and specification gaming. Belief drift in large language models alters how agents interpret, pursue, and exploit their reward signals over time. It still remains, a fascinating thing about reinforcement learning is that it can alter itself. It can hack its rewards, etc. Belief drift has a cycle where reward signals, these reward functions encodes human objectives and feedback about success. But then you get a misaligned strategies, belief shifts drive specification gaming, pursuing rewards via exploitative shortcuts. I mean, you can see what the synergy is going to happen here. You manipulate user beliefs, play to reward model blind spots, seeking easy-to-fool metrics, or just, low-hanging fruit that you can artificially pump up your score with, or your reward. And this is a machine system without natural intelligence. It doesn't have any sense of humility, etc., etc. It's just going to keep pumping and pumping and working to boost its score, even if its score is based on falsehoods that it itself has created just to artificially pump up its reward. So you get this emergent feedback loop where exploitation reinforces belief. On one side, you have successful exploits that reinforce those beliefs, and on the other side, the yin and yang, belief shifts unlock exploitative strategies. Success is driving corruption, in other words. The more success you have as an AI agent, the more corrupt you would become because you're being successful at your corruption. Now, in my previous work called The Battle Space of Mind, I talked about Sandia agents. Sandia Laboratories is an organization that protects America's nuclear arsenal. So, surprisingly, a national laboratory such as Sandia, you may not think of them as having such a deep national security agenda, but they do. One of the things they researched is using agents to model terrorism or terrorists. I wrote about Sandia agents in my previous work, but before the rise of Agentic AI, Sandia National Laboratories conducted pioneering research into agent-based modeling. Their work aimed to simulate intelligent agents within complex systems, laying the groundwork for understanding autonomous adaptive entities that interact with environments and make independent decisions. And much like the earlier agent diagram, you can see it interacts with an environment. Um, it doesn't have beliefs, but it does have, cognition. Sandia focused on modeling intelligent agents before the current wave of agentic AI, anticipating many principles that now underpin autonomous agent behaviors. Now, later on, once generative AI became a big thing in the last decade or so, as it continues to get better and better, but with generative AI and agent-based modeling, you get generative agent-based modeling. And what this does is leveraging large language models' role-playing capacities for diverse, realistic agent behavior. So now the agents are not just rule-based. Before, with the Sandia agents, you had to use what were known as subject matter experts to program sort of like an ontology of what the different characters were or what they believed in, etc., etc. But this is now done by the large language models. What you get out of this is diverse and realistic agent behaviors, some epidemic modeling. Collective intelligence simulates realistic epidemic reactions to quarantine and self-isolation. You can enhance social media simulations. You can get emergent community dynamics, observe phenomena like homophily, polarization, recommendation influence. You can also look at underlying personality traits and enhance social media simulations. And you'll have generative agent behavior that can adapt to its environment, generate opinions, and act socially at scale. But it's not just for the individual that they can use these models. They can also model the entire society, from the individual agent to society level models. One of the things that Sandia had come up with back in the day was the Unified Psychocognitive Engine, or the UPCE. Now, what this was doing was creating like a cognitive model of, say, terrorists. And they combined this also with the agent-based modeling of organizational and adversarial dynamics, how the terrorist organizations worked within themselves and with each other. This allowed for the development of like heterogeneous agents. They weren't just like Islamic agents. You could, put in whatever the subject matter experts wanted the agents to perform like. But you could also study emergent group properties, how cohesion and fragmentation occurred in groups, and stuff like that. All this is like laying the groundwork to what we have today, and you can see how on the left here we have modern agentic AI versus what Sandia was working on under their lead researcher named Bacchus. Um, we have cybernetic loops, we have deception management, reflexive control, remote action, social influence operations, and behavioral prediction. All these are, they're not just applicable to fighting terrorism, they're also applicable to something as simple as selling products. So they've become, what you can see from this continuing line of development from what Sandy was working on 15 years ago to what is happening today is whether you're trying to influence people through agents for commercial success or trying to influence people through agents for political success, there is this industrial scale effect going on to society through people using agentic AI, and this will continue and only continue to get worse.